is let's say we have a beam here, right? We said you have a beam, you know, as a rigid body is supported this area and then this area. Point loads. Right? This was the kind of load that we were working with. It's like, oh, one load could be here, the other load could be here. We could have some moment, right? M. We could have couple, you know, somewhere here. So that's what we talked about, right? But in reality, what happens is that we have distributed loads, meaning that the load we have in reality are not are rarely point loads. What you see, for instance, when you have a box on the floor, I briefly mentioned, I referred to that. When you have a box on the floor, right, something like this, when you have this box, I shouldn't probably. A contact area between the box and the floor is an area, right? It's not a point. That means the force or the load applied by this box on the floor is a distributed load. You can think about it this way. That's how we usually represent distributed loads. If the mass is distributed evenly, it's going to be distributed. If, for instance, when you have snow on the roof, right? Snow on a roof is a very good example of a distributed load, right? You have this snow distributed on the roof, depending on its what kind of roof you're dealing with. This is not a point load, right? You can't just say, oh, I have snow on the roof, like a roof like this, and if there is a snow on it, it's as good as I can draw snow. It's not like just one point load, right? It's not just one load here. I can do this. It's a distributed load, right? The load is distributed on the area. So the force it applies to that surface is a distributed load. So hopefully that gives you a sense of what I'm talking about here. Most of the loads in engineering we deal with are distributed loads. All right. So how do we deal with them? If we only learn how to work with point loads so far, what does that mean? It means we have to throw out everything we've learned about point loads and look into how to work with distributed load? No, right? Obviously, we wasted the whole semester then. What we do is that we try to, or what we do is that we find the equivalent of distributed loads, right? Let me formalize everything and write it down. So distributed loads, right? Write it this way. Distributed loads can be the weight of the material, right? Caused by wind or hydrostatic pressure. What do I mean by that? Caused by wind is, imagine you have a tower, right? Wind turbine, right? Very high. What happens is that when the wind blows, right, this way, it pushes the whole structure, right? It's like a load distributed along this tower, right? So that's a distributed load. There's not just one load. Hydrostatic pressure, think about the water behind a dam. Right? If you have a dam like this, and you have water behind it, right? This water, well, as you see, the reason we can generate electricity from power, it has some energy and it's pushing this dam, right? It has some pushing this dam, this one. Now, that's also distributed load. So these are like real world engineering examples that you have to take into account distributed loads. There is no way to avoid distributed load, right? I think I can just keep them. So how do we do that? As I said, we replace distributed load with concentrated load, which or point load that we have been dealing with so far. I'll say, well, what happens is that once you have this distributed load, we'll say, well, I know this is a wind, let's say turbine tower, and wind is blowing. If you know the distribution of this distributed load, the way it's distributed along this tower or the way it's distributed along the dam for water, you can actually find the equivalent concentrated load. That's very bad handwriting. I can try it again. Concentrated load or point load, as they call it. All right. Now, how do we calculate that? Assuming that we know how the distributed load is distributed along some area, well, we use what we learned for centroid of the area, right? We treat the distributed load, the profile of distributed load as an area, and we find the centroid of that. That would be where we put the, because what is challenging is where do we put this concentrated load, right? You'll tell me, well, okay, so concentrated load would be the distributed load multiplied by the area that is applied to, that gives you the load, total load. But the question would be where to put it, right? If you put it, how far you have to put it. So this is the distance. Where should I put it? And that would be the centroid of the area for the profile of the load. Explaining too much. Let's just put in 4 words and then we'll look at an example. We can replace distributed load. And this is something you're going to do a lot and very frequently in solid mechanics, introductory solid mechanics, and machine design also a lot. Because as I said, these are like real engineering situations. You have distributed load and you have to find the equivalent for that. Distributed load with a concentrated load, the magnitude of this load is equal to the area under the load, right? Load curve, as we call it, the profile of the load, and its line of action passes through the centroid of, let's say, that area. So, oops. So when you have a distributed load, right, you need to figure out two things. You need to figure out two things. Right? You have to figure out what is the point equivalent point load and where should you put it. So the way you do it, the magnitude, find the magnitude by finding the area under the load curve. Put it in. And its line of action passes through the centroid of that load area. Let's look at an example and do it through an example. It's much easier, so me keep talking about it. So we have a beam. Let me bring the example here. If I know which example is that, which figure is that, 17. So if we have this beam, right, it has some distributed load. We know that this shape, we have the profile. This is load curve, right? This is what we mean by load curve. Load curve, right? Right. So the problem statement goes like this. We say beam supports distributed load, right? That's it. We are asked to find, or better to say, determine the reactions, or let's put it this way, determine the equivalent, determine the equivalent concentrated load. Also find the reactions. This is something from before. Reactions at support. All right. That's what we want to do. Now, let's solve it in two ways. So as I said, we're going to use what we learned, finding the centroid of an area, right? I'm going to cut this. The first thing I wanted to look at this, the way you look at it is that it's a composite area, right? Remember, this is a load curve, and we have to find the area for this. So that's going to be the concentrated load, and we have to find where the centroid for this area is, and that's where we put the load. Right? Basically, we want to get into something equivalent of this, similar equivalent to this. We want to get into this. We want to get into a beam with support at A, another support at, oh, this is a roller. So let me be more. Roller at A, this is pin at B, and one load. We want to go from distributed load to some concentrated load. Our task is to find what is the magnitude of this load, and where should that be located from one end of this beam, one way to any, with respect to any reference, either point A or point B. And that's how we achieve this following what I mentioned in the previous paragraph. We find the centroid, and that's where the load should be located. We find the area under this load curve, and that would be the magnitude of it. Right? So, like any other composite area, we have to decide how we're gonna split it. Right? You can either, so there are two approaches. I'm gonna just try to follow both. Let's start with the simple one. That's something that you might think by looking at it, is that I'm going to divide this. So let me go to the next page and bring it again. Was it this one? Yeah. Let's call this approach 1. Right? I'm going to split it this way, and I say, well, split it this way, and I say this is one segment, and this is another segment. Right? Two simple segments. Segment one, segment two. Segment one is basically a rectangle. Segment two is a triangle. Let's form that table. And remember, in this case, I'm only trying to find where this load should be located along this one direction. So I don't care about y. Y doesn't matter, right? Load is a sliding vector, can be anywhere in this direction. So all I'm trying to do is that I'm finding this. Let's call this x. I want to know where, how much this concentrated load should be, magnitude of that, and where should it be located. So I'm going to form this same table that I used to form, but in this case, I only care about, well, we have segment one, we have segment two. And let's call this segment one, maybe do it the other way. And let's call this triangle segment one, and call this rectangle segment two. So I'll put it segment, area for that segment, x bar A. Area would be, well, this is meter, so area would be meter squared, x would be meter, and x bar A would be m cubed units. Segment one, right? What is the area? Well, it's a triangle. Can someone tell me what is the area for segment one, the green segment? I'm looking for the area for segment one. I'll wait as much as time you need.
Would it be 2? 6/3?
All right, so maybe it needs some explanation. So look at the load curve, right? This is our load curve. And we split it into two segments. Segment one, that's not what I meant to do. Segment one and segment two, right? This would be the base, which is 4,500 minus 1,500, so 3,000 here. This is 1,500 Newton per meter, and this is also 1,500. Right? This is the profile of our load curve. This is our load curve. Right? We look at this load curve the way we're looking at the composite area. Now, looking at this, and you know this side is 6 meters. Now, looking at this, what is the area for this triangle? Segment one. Area of the triangle, because you have the base and a height. How do you calculate the area of a triangle knowing its base and its height? All right.
Professor, I'm sorry, but I could totally just be missing something. I only see the 6 meters.
But you do see 3,000 as the base, right?
I see the forces, yeah.
So as I said, the load curve, we treat this load curve as like a composite area with loads being the dimensions in this direction and typical dimension in this direction, right? Because the area here, right? Now I see why the confusion is happening there. Let me change the units. Units are probably causing the confusion. This is meter, right? Area here would be Newton. And X bar A would be Newton, let me put it this way. Meter, and then, and this also becomes Newton. Right? Maybe that clears that up. This becomes Newton meter. Maybe the units were confusing. So Newton meter. That should make it better. Area now is the force, right? As in this paragraph, we said the magnitude of the load is equal to the area under the load curve. So the load curve, whatever is the area, would be the magnitude of this. So what we're trying to find is the area under the load curve. Now, whenever I talk about area, when we deal with distributed loads, it means we multiply the distance by distributed load. Like distributed load is Newton per meter, 4,500 on the right side, 1,500 on the left side. So take what you learned from composite area and apply it to this case. Now, only difference is that now you have one side in terms of length and the other side in terms of distributed load. So the area of each segment is basically a force, which shows the magnitude of the equivalent concentrated load. What happens is that once you find the area for this triangle, that area represents the force you could put at the centroid of this triangle as the point load. So that's some kind of force. Let me continue this, maybe it makes more sense. So this becomes 6 times 3,000 divided by 2. That's 3,000. Let me write it top. 6 times 3,000 divided by 2. You'll get 3,000, 9,000. 9,000 newtons.
Professor,
Go ahead.
you just mixed up your numbers. You have 600 times 3.
Oh, yeah, it's 3,000. All right, it's 3,000 times 6 divided by 2. Now it's correct. So it becomes 3 times 3, 9,000. That's Newton. Right? It's for segment A. Now for segment B, our second segment, I would say 1 and 2. Segment 2, we have 6 meters times 1,500 is the height. So it becomes 6 times 1,500, whatever the value is. I think it becomes 6,000.
I got 9,000 again.
9,000. Yeah, it becomes 9,000. All right. Now remember, this is now Newton because we are looking at the load curve. Right? We're treating it as like an area, what we learned before. But now with dimensions, one is length, the other one is load per length. X bar for this, right? Let's assume that we take the origin of our coordinate system here. You could take it on the other side. It doesn't really matter. You're going to end up getting where the distributed load is. Now, if we take this as the centroid, right? Let's say segment 1. Now, segment 1 is this triangle, right? This triangle, we are trying to find, let me put the coordinate here. This is x, this is y. We're trying to find where the centroid is in this coordinate system. Remember, for a triangle, I can find how far this centroid is located from the base, and that's 1/3 of the height. So height is 6 divided by 3 is 2. That means the value for x bar, if I take this as x bar in my coordinate, x bar for segment 1, that's 6 minus 2, it becomes 4. For rectangle, you will get, let's say the centroid, well, centroid is exactly in the center, right? So this distance would be 3 meters, which means your x bar is 3 meters. This third column is just basically multiplication. 4 times 9,000 is 36,000. 3 times 9,000, 27,000. Now you're trying to find the center at which the distributed load should be applied. We're trying to find two things. Remember, this is what we're trying to figure out. This is the beam. We are trying to find out, this is A, this is B. We're trying to find out where this load is located, if you want to put just one point load, and what is its magnitude. It's equivalent. We said we're going to convert distributed load into point load. This is what we're looking for, which means I need to know what is the value for P, and I need to know how far this is located from one end. Right? So just call it XC. If this is X and this is Y. So P, as this paragraph says, it's the equal to the area under the load curve. So area under the load curve is just summation of these two areas, right? It's like 18,000. So P is equal to sum of all the areas is equal to 18,000 Newton. So that P is 18,000 Newton. Where it's located is sum of x bar I AI over sum of areas, right? That would be the sum of these two, x bar I AI, would be 36,000 plus 27,000, 5,000, 63,000, right? 63,000. So then you have 63,000 divided by 18,000. That'll give you 3.5 meters. That means that this is located at 3.5 meters away from point A, the origin. This is what we were trying to find, right? The load and where it's located. Once you know this, the second part is asking you to find the reaction forces that supports, right? For reaction forces, well, now this is what you have. Now you have a beam. I get point A. It's a pin. It's a roller. Let me use a different color. It's a roller. At point B, you have a pin support. So you have to put two forces. So AY. This is BX and this is BY. And the load is located at somewhere here. And you know the distance is 3.5 meters. Though I guess I'm just really overblowing it. It's more close to the center. So somewhere here. This would be 3.5 meter, while the whole thing is 6 meters. The rest is what you learned from before, right? Summation of forces in x direction is equal to 0. So Bx is 0. Summation of forces in y direction is equal to 0. Take this as positive. That will give you Ay plus By is equal to that force we found is 18,000. So it's equal to 18,000. Now we have to write the moment. Equation of moment, let's write it about point A at this point. It doesn't really matter A and B because Bx is 0. If you write that, this becomes 6By positive minus 18,000 minus 3.5 times 18,000. Negative is equal to 0. From there, you can get your By and your Ay. You'll get By as 10,500 Newton and Ay as 7,500 Newton. This part is something we learned from before, right? We knew how to deal with beams and objects, rigid bodies under loading with different types of supports, as long as the loading was typical load or concentrated load. What was new was that when we have a distributed load, like in this form, when we have a distributed load like this, the procedure says treat that as a composite area. You have the dimensions, you know, the distributed load values. The only thing changes is that units are different, but the procedure is the same. You find the centroid of the area and you put the concentrated load exactly where the centroid of area is. Now, centroid of the area where the concentrated load should be applied, and the load itself is equal to the area under the curve.